in designing and innovating many components as well as spectrometers at Cyrus and Dhruva, and subsequently. For example, he initiated small angle neutron scattering studies at BRC, for which he designed and built a science instrument at Cyrus reactor in those days, and now we are taking advantage of this at Dhruva. He has also made a series of innovations. I don't want to list them in terms of detection system, the windows, and so on. And one of the key innovations was the use of polarization dependence of inelastic coherent scattering to capture the vibrational motion in. So this was the first of its, and he has a very over 200 editors, and he has PhD students and MPhil students. He joined and rose to the level of director of physics group, and he was heading 3 different divisions. Divisions in BRC, solid state physics division, division, and plasma technology. He has been recipient of several awards, including Mahendra Sarkar Award of the Indian Association of Cultivation of Sciences, Homi Jahangir Bhabha Medal of INSA, and ANSA Prize, very prestigious ANSA Prize. He's a fellow of Indian Academy of Sciences and Indian National Science Academy. He has served on many committees, council of INSA, etc., and he has distinguished himself by mentoring a large number of young researchers, and I am one of those beneficiaries. He introduced me. I mean, I'm personally very happy to chair this. I mean, I feel honored to chair this session where Dr. Dasannacharya is going to speak. He initiated me to do neutron-based research, and it made huge difference. I mean, when I started it, I didn't know much about in what way neutrons can help me, but he guided, and then we never looked back since then. And with these few words, I have great pleasure in inviting Dr. Dasannacharya to give this Neutron Scattering Society of India lecture on the memories of neutron scattering in India. And this is a very fascinating topic. He's a very distinguished speaker also. So, Dr. Dasannacharya.
This is the one which press for just touch. Just touch it will go. Straight up, straight up. There you go. This is page up, page down. For laser pointer निवडते ठीक आहे page down. Okay. First let me pardon just gone off. So wait for 2 weeks. Yeah. Till the project comes on, let me say that in the introduction, I find it very embarrassing because half my talk has been delivered in the, and I'm happy the projector is not on. so I can speak to you like this. But nevertheless, what you prepare, you have to deliver. So I'm going to talk about it. Is the projector, when the projector comes on, tell me, then I'll start my lecture. Is the projector on now? Not yet. I will tell you a story of Sir William Bragg, the younger Bragg. He was visiting from the Royal Society, Bombay. He gave 2 lectures in TIFR and 1 lecture in BRC B block. And there was a gentleman who was the head of the chemistry division at that time. Being a Parsi priest, he used to wear a hat, which was very distinguishing. And so he attended all the 3 lectures. So after the 2 lectures, when he to attend the second lecture at TIFR, it was the same lecture which he was going to give in B block. So he pointed out to him and said, "Look, you are attending all the 3 lectures. I have prepared only 2. What I talked in BRC, I'm going to talk here again. So if you want, you can go or you can do whatever you want." So in the same vein, let me say that whatever I'm going to talk, see beautiful slides, micro presentations and all that. What I'm going to, introduced by people, I will start something which is 60 years ago. The presentations are all old. So it's nothing like what you've seen. But I will say, for whatever it is worth, I have a point to make. I hope that will be clear by the time I finish this talk. So it's not just the science behind it, but the spirit behind it. So let me start by saying, is the projector on? Yes. It's a matter of great honor that the Neutron Scattering Society of India has accorded me the privilege of delivering the first neutron scattering lecture. I want to emphasize an honor by the near and dear ones is the sweetest that one can receive. So I'm particularly obliged and happy about this to the Neutron Scattering Society of India, which is my own society. Like Professor Dhananjay Pandey said that he is from my university. I want to object. Dhananjay Pandey is from my university. As this is the first lecture of the series, I thought it may be appropriate to recall how this subject was seeded at Trombay and nurtured into fruition over the next 4 decades or so. Now the total period is 60 years. I will probably talk about 45 years, last 15 years. So I shall do this by taking examples from my own activities with many of my colleagues. I say my activity, but it's the activity of the whole sort of. I make no effort to give an exhaustive account, as it is anyway impossible to do in 45 minutes. Most of you will know that Homi Jahangir Baba was responsible for the advent of atomic energy in India under the benevolence of the then Prime Minister Jawaharlal Nehru. Now, Baba was a very extraordinary person. He returned to India from Cambridge. He went to Cambridge when he was 17, did his graduation in mechanical engineering, but he decided that he has to shift to physics, did his PhD in physics, and worked out the theory of extensive air showers of cosmic rays and predicted the presence of a meson. He returned to India in 1939 when he was 29 years old. But at that time, he was already on the verge of fellowship with the Royal Society. He joined IISc, was there for 6 years, proposed that we should start the Tata Institute of Fundamental Research, and at the age of 35, he started that institute. At the age of 42, he started a Department of Atomic Energy, and the rest is history. To start with, Bhabha chose a small team of scientists and engineers to translate this grand vision into a practical program. H.N. Setna, Barn Prakash, N.B. Prasad, A.S. Rao, Ramanna, and Gopal Iyengar were the prominent members of this initial team. Ramanna was the chosen person to usher in R&D in physics in Atomic Energy Establishment, Trombay at that time, now BARC. Again, Ramanna, when he came here, when he joined BRC, he has done his PhD, joined Department of Atomic Energy age of 27, and as I will show you, in another 4 years or so, he essentially became in charge of the nuclear physics research, R&D, in the DAE institutions, mainly BRC and a bit of TIFR. So again, I emphasize this, that it was at a young age of 31 he took charge of this. He was a nuclear physicist with a specialization in fission physics, but was given a mandate to develop a broad-based research program in AE. How this was done, as far as neutron scattering is concerned, is the subject matter of the present talk. Before I go into that, let me spend a minute to describe the necessary requirements for developing an extensive area of experimental physics. It is a truism that growth of modern science, and especially physics, is synonymous with development of tools of observation to check out certain ideas directly, or to make observations leading to ascertaining the same, or to find new ideas. This has been well expressed by the grandfather of modern Indian science, Jagdish Chandra Bose. He said, and I quote, "The first condition for advancement of knowledge is great imaginative faculty. Two other conditions for successful prosecution of research are the facility of a well-equipped laboratory and B, the invention of new equipment of extreme delicacy and precision." This is J.C. Bose talking around the beginning of last century, 2000. I have also presented a similar view in my article in Current Science in 2015 with a number of examples. I put an alarm to get up from sleep at 3:30. That went off just now. I'm getting up from sleep now. And I have given a number of examples in my article. Not surprisingly, the Nobel Prize in the subject of our present subject, our present interest, was given to Clifford Shull for the development of, this is quoted from Nobel citation, for the development of neutron diffraction technique, and to Bertram and Brockhaus for the development of neutron spectroscopy with special emphasis on constant Q technique. I shall be emphasizing the growth of a part of science based on neutron scattering at Trombay through the development of neutron scattering equipment at BRC. So my emphasis will be more on equipment and less to discuss so science results which we have obtained. I mean, obviously it's impossible, but I have chosen some. At the time of India's independence, there were only 20 universities compared to about 1,000 now. So the number of universities has gone up by 50 times. The number of research laboratories could be counted on one's fingertips. The manufacturing base of the modern kind was negligible with few notable exceptions. However, a wide variety of cottage industries were spread around the country, which meant that throughout the society there were great pockets of excellence all over the place. This heritage embedded in the new type of colleges which the Westerns brought Some produced some excellent results, glorious ones. J.C. Bose, Raman, Ramanujan, they were all influenced by the college education of the Western type. The scene, this is all before independence. The scene changed dramatically after our independence in 1947. The role of Homi Jahangir Baba was important in this transformation. He graduated, I told you about his, he was a great visionary and implementer combined into one. He was able to convince the then Prime Minister of the necessity of going into research and development in all aspects of atomic energy in a big way. And this was not achieved easily. There was a lot of opposition, but then he was able to convince the Prime Minister. One of the first things he did was to decide to get a team of Indian scientists and engineers to design a swimming pool reactor. This is a picture of the swimming pool reactor. How do you get the? How do you get the point here? Hello? Mouse doesn't move. Mouse has gone on a trip. See, this is the reactor. It's a big swimming pool. Typically, it's about 20 feet in width, 25 feet in height. The wall thickness is about 8 feet, and there is a tank which is about 15 feet wide and 20 feet deep. So this is the first reactor which became operational, or rather critical, that's the word used in atomic energy parlance, on 4th August 1956. A fully indigenously conceived, designed and built reactor was ready as a source of neutrons for research, isotope production, and neutron shielding studies. As I mentioned earlier, Baba chose Ramanna to create a team of scientists to work on neutron-based research, while Ramanna's personal interest was in investigation fission. He inducted a number of scientists to work on different aspects of science with neutrons. The idea was to create a viable body of scientists who can research on any problem posed to them. So the emphasis was that you develop a general scientific attitude. Neutron was used as a means to achieve this larger goal. While Ramanna himself was doing fission experiments at Apsara, Nataraj Sarma was given a charge of measurement of neutron spectrum emerging from the reactor using a Fermi chopper received from Atomic Energy Harwell. P.P. Duggal and P.K. Iyengar, who were working with the 1 million electron volt Cockroach water generator at TIFR with Ramanna, were deputed to Canada and France. G. Venkatraman and K. Usha were deputed to work with Peter Ekstaff of Harwell, who was then installing a multi-chopper based spectrometer at NRU reactor in Canada. N. Umakanta went off to AERE Harwell to work with Ray Loud on magnetic scattering. P.K. Iyengar became the lead scientist. Under the overall guidance of Raja Ramanna. I told you P.K. Iyengar was about 27 years old at that time. So he took charge of the activities of neutron scattering when he was 27. He was under the guidance of Raja Ramanna after he returned to Trombay from Canada in 1958. He took charge of this. N.S. Satyamurthy and I joined him in August of the same year. And K.R. Rao joined V.P. Duggal. We were asked to read Bacon's book on neutron diffraction and Shull and Wollen's article in Science and Turnbull, Delaney's article on lattice dynamics, and Slater's Reviews of Modern Physics article on propagation of waves in periodic structures was additional reading. Within 3 months of my joining, I was asked to review this RMP paper, and I was shivering in my shoes when I had to do that. But anyway, it went through because all the listeners were our colleagues only, no public listening. NSS was encouraged, Satyamurthy was encouraged to look at magnetism as he described in his article, some article. The immediate task on the ground was to build an automated powder diffraction to be installed at Apsara. You have heard about this several times in the last 2 days. The basic design was going to be similar to the machine at NRU reactor, Chalk River. It was an old naval gun mount. What you see here is the gun mount. This is about 2 feet in size, and it is taken from a naval ship. So 2 gun mounts were bought from the naval dockyard for practically no money. They were thrown. And this is the way, on top of this, a detector arm was mounted, and this is what is called the theta to theta arrangement. So that when the detector moves by 2 theta, the sample will move by a theta. This is the standard requirement of a diffractometer. The counting and automatic control electronics using a uniselector switch and relays had to be done between electronics production section and in-house by us at Atomic Energy. It was all completely new to me, especially as I had joined after completing BSc and 1 year of theoretical training at the training school. Iyengar's friendly guidance and friendly colleagues made it that much easier. It was ready for installation at Apsara by the end of 1959. So in a matter of 1.5 years, we were able to get the spectrometer sort of working. The monochromator, a large cylindrical aluminum crystal, was placed inside the provisional neutron shield. Neutron shield is not visible in this, but it is somewhere here. Monsoon period between June and September in Mumbai is very high temperature and high moisture and not friendly for the electronics, which was kept in the Apsara hall, which was not air conditioned. Minor incidents like uniselector switch catching fire a day before the visit of Prime Minister, and our discovering just before installation that our primary collimator was too big for the beam tube added to the confusion. We had to resort to emergency machining in the neighboring mechanical workshop. However, thanks to the prevailing informality those days, it was possible to get the first diffraction pattern for calibrating the diffractometer. This was followed soon by the first diffraction pattern of our research sample FESN2 in 1960, which was reported in Japan and published in Journal of Physical Society of Japan. Actually, this caused a lot of interest. This is a very small experiment. I'll show you for the sake of, that's the diffraction pattern. You will see here there is antiferromagnetic peak, this one. No, this is the antiferromagnetic. Where is it? This is the antiferromagnetic peak, which is on heating. This is at 200 degrees. It vanishes at 420 degrees. So it was able to prove that this is antiferro. This was the first measurement, and we proposed a diffraction structure which is like this. It took us more than a day with repeated runs to record the pattern. The exhilaration which I felt in observing the antiferromagnetic superlattice is still fresh in my mind. It was by no means a major result, but the fact that we had a definite observation of antiferromagnetism, which could be done only by neutron diffraction, gave a kind of satisfaction which is hard to describe. Such are the moments one cherishes. Other laboratories in the West followed with diffraction of FEG2, FESN2, etc. I note in passing that this was the first automatic counter-based diffractometer built in India. And this has been mentioned several times. So now I go to the first phonons. A diffractometer had been ordered from John Curran and Company. The person who ordered left BRC, and that came to Iyengar. So he used the ingenuity to convert it into inelastic scattering machine. You will see this. This is monochromatic drum. It should have, normally it would send the beam to this point. So what we did was added a channel here like this, a cross channel like this, which was moving on in this. So by moving this place, you can move the scattering angle, and the crystal was mounted on this. The analyzing crystal went where the sample was supposed to be mounted for diffraction. So with this simple device, a two-axis machine or a diffraction machine was converted into an inelastic scattering machine with a very minimum of mechanical. The first diffraction phonons which were measured is shown here. It was reported at IAEA in 1961. I think these two phonons which are shown here are dubious. This dashed line is, at that time we were thinking it's not right, but now I think even these are not right, because the intensity was really very small. So this is like you look for, nowadays you look for a small pit in experiment in high energy physics and so on, but it was nowhere near that, but it was a question mark. Now it's limited. I go to Cyrus. Cyrus reactor was designed and installed by Canada under an intergovernment agreement with India. It was like the Canadian NRX reactor. It has a central flux of about 1.8 into 10 to the power 13, which is similar to our Cyrus reactor. It is 2 orders magnitude better than Apsara, but even then, it was not the highest flux reactor in the world. I mean, NRU was already built. Anticipating the starting of the new reactor, the two machines at Apsara were shifted to Cyrus. The John Curry machine was installed as a powder diffractometer. So it was converted back to powder diffractometer. The diffractor built on the gun mount was converted to a beryllium detector spectrometer for inelastic scattering studies by installing a beryllium block in. So in that, what you do is in front of the detector, you put a beryllium block, and what it does is only allows neutrons below 5 MeV to pass through. So it's a filter, which is the kind of Raman used to do in optical experiments, putting green filter, violet filter, and so on. 3 more instruments were ordered to be built by New Standard Engineering, and one of them was made into a triplex spectrometer. This is the picture of that one. This design is very different. It's not based on the gun mount. It was based on a basically design of a radial drill. This is the stand of the radial drill. This is the sample, comes here, and there is, after a shield, it goes to an analyzer crystal, and then there is a detector. So now this is the third spectrometer I'm talking about in 1960 or 61, in a matter of 3 years or less. G. Venkatraman and Usha were busy building a rotating crystal spectrometer, which is very similar to the one built by Brockhaus. It produces pulses of neutrons of 4.1 angstrom, a number of them, and the spectrometric spread is, after the scattering, is measured using a time of flight technique. An incident energy of 5 MeV is quite low and largely measures the spectrum of neutrons which have gained energy or up scattering. Like in Raman scattering, we have Stokes and anti-Stokes. You don't see both the lines in this, you only one side, the gain side. Compared to the triple axis spectrometer and the filter detector spectrometer, RCS is an instrument with better energy resolution in small energy transfer, but poorer intensity because the resolution is tight. Using the filter detector spectrometer, one measures only the energy loss, because there the analyzing side, the energy is fixed at 5 MeV, which is small, and the incoming energy is always large. So in FDS, you measure energy loss. In RCS, you measure energy gain. And with triple axis, you measure both energy loss and energy gain. They are all complementing each other. Thus, a full suite of inelastic scattering was available in 1961-62. The results from the 3 instruments were reported in IAEA conference on inelastic scattering at Chalk River in 1962. This is what I said, and these are the results. This is phonons from magnesium, which was done using triple axis machine. This is rotation in ammonium chloride measured using a beryllium detector, and the same ammonium chloride studied using rotating crystal. These high energy modes are shown here, and the elastic scattering. So essentially, the point I'm making is by 61, 62, that is within 3 years, these three instruments were functioning and giving results. All three spectrometers were functional. I did experiments there. No, at this time, I was deputed in August 1961. I went away to Chalk River to work with Brockhaus's group. I did experiments on temperature dependent germanium and liquid argon as already. So after coming back, having worked on liquid argon, I proposed that it would be a good way to work on liquid methane, which is a spherical top molecule. So like argon, it's all isotropic. There are no angular effects. In addition, there was a suggestion from an existing filter spectrometer instrument that in liquid methane, near its boiling point, there is free rotation. So it should be like you see in a rotational spectra, you see rotational lines. So it was suggested that there should be possible to see rotational lines. We tried this using rotating crystal spectrometer. We worked out what the spectrum should look like. This is the theoretical spectrum in which the elastic line has been broadened by resolution and the diffusion coefficient. Diffusion broadens the resolution line, and it also broadens every rotational line. These are the rotational lines corresponding to 1, 0, 2, 0, 2, 1, 2, 2, 2, 0 transitions. And if given our resolution, the high resolution of rotating spectrometer, we should have been able to see this. This was not possible in the data, which was taken for days together with an improved resolution of the machine by going to smaller angle and putting a collimator. So we knew how to manipulate the machine. Essentially, when we wanted to go to low resolution, we did how to do that. So this is the result which we published, and this was the first result which was used by Sears in Canada to correlate neutron, Raman, and infrared results, which we extended a little bit more to fourth order correlation. As I said, I'm taking simple examples from different places. There are lots and lots of experiments which were done on RCS in the following time. Very soon after this, we worked on liquid crystals. Liquid crystals in all their phases, nematic, smectic, and isotropic, with magnetic field, without the magnetic field, and momentum. This is something which can be done only with neutrons. But okay, I'm not talking about those things. And then we spent a number of years looking at rotations of ammonium molecules and things like that. But this is a simple example which started off the rotating crystal spectrometer on a good note. Now I'll take the second example, which is on the beryllium detector. I shall now give take the case of beryllium detector spectrometry. Here the analyzer channel is a beryllium block. This allows all neutrons below the beryllium cutoff. How many minutes have I done? Where is the clock? Sorry, I didn't keep my clock. Chaplo, do you have any idea? Huh? 15 minutes. I've already taken half an hour. Okay. I want to point out in this, as I said earlier, beryllium detector spectrometer, the outgoing channel, you allow all the neutrons below 5 MeV to pass through, which means the wave vector is uncertain because you have all the wavelengths from 4 angstrom to infinity going through the detector. And therefore, it was believed and standard acceptance that beryllium detector spectrometer cannot be used for measuring dispersion relation, especially if the dispersion relation has a big slope. Now, what we did was we worked out the resolution of a BDS on the pattern which was already known for triple axis spectrometer by certain modeling. And we said, okay, we will measure the shapes and we'll calculate those shapes of the phonons at each place and see how it goes. So the inelastic scattering spectra which were measured using the beryllium detector, the results are shown here. You see the slope is given at the side here. This is longitudinal acoustic, longitudinal optic. This is longitudinal acoustic. This measurement has not been made. But you see here in this particular case, these are pretty close to the peak, what you take as the standard frequency. But in this case, the peak appears here, but the frequency is here. Now, this is something which you can simulate easily if you know the resolution. So you have to work, if you want to do beryllium detector spectrometer, you have to work with the resolution calculation. Now, this is common nowadays. This is common nowadays, but it was not so all the time. So, but you may say, why do you want to take all this trouble? I'll tell you why I took all the trouble. We made measurements of phonons in beryllium using triple axis machine. We could not go above 13 frequency of about 13 terahertz or something like 13 into 4 or 54, 55 MeV, because when the phonon energy is large, the incoming energy of the neutron becomes large, intensity comes down, and so with whatever combination of incoming and outgoing energy we could do for triple axis machine, we were not able to go, we didn't have enough energy. These are all the phonons shown measured on the beryllium detector spectrometer. And as you can see, the slopes are quite large, both in optical and you could go right up to 20, that is 18, almost 82, 83 MeV. This is impossible. This was impossible for us to do without the BDS at Cyrus. And in fact, our results compared very well, or rather better than the time of flight measurements done at Idaho Falls by their group. Now, the only point I'm making is sometimes you give away a certain instrument saying that it's not possible, but with the ability of all the software which you can put. So today's instrument is not an instrument as just hardware. You have to combine the two and get the best out of it. And that happens continuously these days. All the results which we see, there are a lot of software which goes on. Now I'll go to the next one. 15 minutes. I'll talk of what is called the delta T analyzer. This is just a show by 70s, Cyrus reactor, full of instruments and growing. I shall not this shows on the y-axis you have the energy width, on the x-axis you have the neutron energy, 1, 2, 3, 4, 5 MeV, and the delta E is shown on the y-axis. You see all the instruments which exist in the world, they lie between the two straight lines. In other words, at lower energies of 2 MeV or something, they will give you a better resolution. As you go up to about 5 MeV, to get a resolution of that kind becomes impossible. All instruments, BNL, this is in BNL instrument, this is at ILL, NBS, this is at ULISH, and so on, so on. But what we do with the delta T spectrometer is to produce an instrument which can give you a resolution out here, which is far below this at this energy. Now, if you are able to reach this kind of a resolution, it is left to your imagination what physics you can do. There is a hell of a lot of physics you can do. This instrument has not been completely utilized to its capability. I would have liked to give a little description of this instrument because we spent a lot of time validating this in this, the analyzer was essentially a window filter with beryllium, cooled beryllium and hot beryllium, and the energy resolution of the incoming side was provided by the time of flight as suggested by Bose. So combining these two, the analyzer would give about 20 microelectron volts at 5 MeV. The incident was another 20 microelectrons because of the long flight path. And so you will come with a resolution which is about 40 microelectron volts at 5 MeV. No other instrument. It was accepted. The result of this proposal was Rutherford Appleton Laboratory accepted this. Because of this, they put up a hydrogen source, which was not earlier likely, and a new beam hole was opened. More important than that for us, for our purposes, these are all validation process, how the resolution is measured. This is the instrument which actually was sent to Rutherford Appleton Laboratory. And this is the measurement which is done on NH4. This is just a demonstration. And 40 microelectron volts predicted width. And this is the measurement made on NH4Br, which could not have been done on the Triplex or any of the other inelastic machines which we had. I think the more important point of this was, let me also say that theoretically you can predict. I mean, theoretically it was possible to say that it will happen. To show that it actually happens, we had to do a number of validation experiments. We had to see what is the width of the beryllium. These are the favorite things which one talks, but as Chidambaram said, when you want to save time, throw away your favorite slide. So I'm going to throw it away. But essentially, I'm saying this has still potential. If one can think of new ideas, one can use this detector. Most important thing which happened as a result of this, BRC or rather India and Rutherford Appleton Laboratory start collaborating. Our scientists were able to go to Rutherford and use any of their instruments, not just this, any of their instruments. So a lot of opening happened for the next maybe 15, 20 years or so. Leave it at that. I will not talk about SANS, which was mentioned. It's again, lack of time. On to Dhruva. Higher flux, better beams, lower backgrounds, better beam optics, improved instruments, more position sensitive detectors, more Q omega space and better resolution, better intensity. So for all these reasons, a new Dhruva was proposed. This was in 1973. 1973 beginning, Department of Atomic Energy decided to build a 100 megawatt research reactor in early 1973. Physics group was asked to specify its requirements for neutron scattering research. Iyengar asked me to make a proposal after consulting all the colleagues. Venkatraman had attended the Nobel meeting on neutron scattering in 1972. This conference was held soon after the new reactor of Grenoble became operational. That is the ILL reactor, the first ILL reactor. GV presented this conference, reported at a colloquium, and gave details of the layout of the beams. This reactor with enriched uranium is different from Dhruva. But some ideas can be adapted. Dhruva is a natural uranium reactor with D2O moderator and D2O reflector, and coolant has some basic similarities with NRU reactor. A detailed layout of the neutron beam channels is shown here, which was finalized before I left in end of 1973 for Ulish. Some of the features are the follows. There are 4 tangential beam tubes, these 4, which don't look directly at the core. So the gamma ray background is low compared to the neutron. So that is one thing. But the moment you make it tangential, the length of the tube goes on, so the flux comes down by 1 upon r square. So to do that, we pushed the concrete shield inside and steel shield was provided so that the length of the tube again was brought. So we not only reduced the gamma ray, we did not allow the neutron flux to go down. That was one thing. Of course, then there were provision for cold source and a guide tube lab and a hot source and so on. But another interesting thing which I would like to comment upon and which I was very proud of introducing is these insertions in the beam tube. This through tube is similar to what one have at NRU. But you open this insertion so you can put the monochromator inside. The first powder diffractometer was put on this beam. This is a 60 degrees, gives fairly good resolution, and the first and the Max Institute instrument is put on this, which therefore is able to. One of the things about this is this it sees a scattering from a D2O here, so it goes closer to the scattering source. Again, you pick up the flux. So these are the features which are there. I will not go further detail for lack of there are cold source and hot source. So I went away in 73 to Ulish, and Dr. K.R. Rao took charge of various things. My interest was mostly because it was clear to me by that time that position sensitive detectors, focusing spectrometers, these are the things which should form, and big detector should form the future of neutron scattering. So there were 4 or 5 instruments: Max PSD based powder diffractometer, large Q. This I encouraged Paranjpe to do this. This was done by Mukhopadhyay. This was done by Rangamani, and now later by Shivaram Krishnan. And this I will talk to a little later. Yeah, that's what I take. The last one. Of course, I must point out here. I think I have. There is. I don't know where this has gone. Oh God. Oh, I had a slide showing all the instruments, but okay, it's missed out. So that has been replaced by this. Anyway, let me talk. It was in 1994, one of the IAEA meetings, which was held in Budapest. I made a proposal as a suggestion that these are the 3 things which we need to care about. We must improve the neutron economy. That means neutrons which are coming from a beam tube, why should they be used only by one instrument? Improve the neutron economy. We should improve the resolution. We should improve the intensity. Some of these requirements seem contradictory to each other. But if you understand your instrument properly, you can indeed get over these problems. And my preliminary solution was that from the source, you take a beam and you put multiple monochromators, 1, 2, and through the main thing, you can take another instrument. Now, one thing is, if you have this, you cannot put solar collimators, because solar collimator requirement of one instrument may be different from the other. So you work with open geometry. Now, we had no experience with open geometry, so we decided to do a Monte Carlo calculation for this. Now, what is shown here is you have a triple axis machine. It is the monochromator, sample, analyzer. You have a powder machine where you have a sample, and a position sensitivity collects all the intensity. Now, this was simulated for so the thing is, you go open geometry, and your collimations, etc., you depend on ideal crystals. Ideal crystals have narrow beams, narrow resolution, so you manipulate. And for the first time in Trombay, we did this. Which is this is the wrong one. Oh God. Yes. So we simulated what the resolution should be if we have an open beam focusing silicon monochromator and position sensitivity for increasing intensity. And we found, to our surprise, that the the resolution full width at half maximum which we get is excellent with this combination of focusing beam and not only that, this is fairly flat. The resolution over a large distance is fairly superior. And when we actually, the instrument was built, which was shown in the previous this is the instrument. This is the channel where the multiple monochromators are supposed to be placed. And this is the detectors. And this instrument, we find that the intensity is more, resolution is good, and it can be used for a variety. So I have a feeling that much more use need to be done of open beam, perfect crystal, and position sensitive detectors. I think some data is shown. This is the one which I wanted to show, but I think for lack of time, I will not do that. Some results are shown, which basically shows that this has a very good resolution. So with these examples, I come to the end of my talk, essentially, with some concluding remarks. Which, what shall I say? What I have written down, I'll read. Solid State Physics Division BAC and UGC DAE CSR have been very successful in getting universities involved in neutron scattering activities. So kudos to both of them. This is a very difficult job needing perseverance on several fronts over a large period of time. And the very fact that Neutron Scattering Society of India exists today is because of these efforts. They need our congratulations and good wishes for their future success. An effort has been made here to show that designing and building sophisticated apparatus is at the root of doing good physics. Therefore, there is a continuing need to upgrade existing instruments and create new instruments. Without this, frontline science cannot be sustained in the long term. In view of the famous theoretical physicist Victor Weisskopf from Massachusetts Institute, quote, there are three kinds of physicists, as we know, namely the machine builders, the experimental physicists, and the theoretical physicists. If we compare the three classes, we find that the machine builders are the most important ones, because if they were not there, we could not get this small scale region of physics. And in machine builders, I include instrument builders. In this context of a neutron scattering program, I think the time is ripe to upgrade old and create new. Groups from universities may be involved in this effort. With neutron scattering community is already of a substantial size, a greater involvement is desirable for a country of our size. As I was listening to the talk, and I want to bring this to the attention of Yusuf, Dr. Yusuf, when we were talking about the beam tubes in Dhruva, at somewhat late stage, it occurred to me that beam tube should be larger than 4 inches. Because when it comes to vertical divergence for neutron scattering experiments, we can accept much more than 4 inches. But by then it was too late. I regretted, and I still regret, that those beam holes. Actually, I had suggested that we should make an elliptical beam tube, which should 6 inches in vertical and 4 inches in the horizontal. But, well, if it is difficult technically or engineering wise, I suggested you have, but it was too late. Now, I am trying to tell now that the Vizag instrument reactor, please see that you have a big enough beam tube so that the whole game is increasing intensity, increasing Q omega space, and improving resolution. And all these essentially means two things: understanding the technique and doing technology. Technology, technology, technology. Only then you can do science. And I am quite sure that all the scientists who are involved in this are quite capable of doing this. So I must wish them well for the next 20 years. Thank you very much.
Dr. Chakraborty,
Thank you, Dr. Dasannacharya, for taking us down memory lane. But I must say that we're really proud of you, what you did. And something 60 years ago, to my younger colleagues who joined maybe in last 10 years, might appear like mythology. But it was something very fundamental. And so I think what you tried to convey, I hope that that will stay with us. And in fact, I personally had the benefit of witnessing at least things from 1975 onwards. So I had seen, for example, the same spectrometer which had been brought from Apsara to and present in Cyrus, and so on. So now, of course, as you said, we do need this hardware and software and an amalgamation of the two in the next generation machines. And I do hope that those will actually be built at the Vizag reactor. Well, I think Dr. Dasannacharya has been introduced yesterday and today, but I just wish to say that the kind of things he did in late 50s was just only a few years after what the Nobel laureates were doing, Brockhaus and Shell and so on. And the kind of things that were done at Apsara were practically like what the rest of the world was also doing. And these were really at the very fundamental stage. Although now there is much more focus on things looking more beautiful, or and a greater focus on applications and so on. But I mean, I think some of the basic things are very important.
For good technology, for good application,
Yes.
good technology becomes even more important.
Exactly. And well, you probably, this was not told, Dr. Dasannacharya didn't receive the Nobel Prize, but he did receive the Asian equivalent of Nobel Prize in neutron scattering, the Eonsa Prize, that we are really proud of. Sir, would you be willing to take some questions? Some questions from the audience. Sure.
But I will take you down your memory lane. I kept something with me. Actually, I have used it for a long time for all my interviews. And this was even before the beginning. And Actually, it doesn't belong to me, it belongs to you. So I thought today is an opportune moment to return back your stuff to you, which I used for last 40 years. This is, I think you can open and you can see. This is before the beginning of everything. Please, please.
Such nice paper. Yes. April 15, 45, 45 by books. One was by standard book and react to and see the second one. Fine. I'm going to spring another surprise on you guys. This young man is here, so he looks much older than what. Present in one book. This is also an old book. Huh? This is the book. It is a memoriam for N.S. Satyamurthy, 1985. He was chosen the president of the physics section of Indian Science Congress. He was to give that, he had prepared the talk, and then he died on October 8th. So he could not give the talk, and we prepared with the Sienna Rao as the chief editor, but I put a lot of effort into this. Since Yusuf is carrying on the legacy of Satyamurthy and Madharao, I wanted this book to be with him. Please accept it. There is an article by Madharao, there is an article by Satyamurthy. Both exhaustive, very exhaustive articles. Thank you.
Particularly your handwritten note.
Yes,
you know?
inside also I have
I'll
written.
preserve this as
Okay.
we do just he is taking one photograph with
Yeah.
your marks. Please put
Yes.
your- Thank you. Thank you so much.
Well, may I ask a question?
Yes, please.
Yes. First of all, I salute you for your great contribution in experimental nuclear physics in India and pray to God for your rest, a healthy and life full of happiness.
Thank you.
Well, my general question I just want to ask, why Professor J.C. Bose could not get Nobel Prize in Physics?
Do you want me to talk about this in an open session with cameras looking at me and all that? If there is a tea time afterwards, I will answer your question. I have written an article on J.C. Bose, and I will send you a soft copy of that if you give me the email. And in the last section of that, I discuss why he probably missed the Nobel Prize. So that's precisely what your question is, and it is my view on that is registered there in that article. It came in Physics News when he on his 150th birthday.
Yeah. So now, yeah, please, our function is not yet over, and I will request co-chair Dr. S.L. Chaplot to hand over the certificate and a memento to Dr. B.A. Dasannacharya. So we'll go there.
Thank you very much.
Yeah, thank you. I'll read it out for you. This side it is Neutron Scattering Society of India, and this is the logo of NSSI, and I believe it was designed by Dr. Wag. So, and with 5 stars here. And on the other side, it is written B.A. Dasannacharya 2021 first NSSI lecture. So this is the certificate. It reads Neutron Scattering Society of India NSSI. The NSSI lecture on Neutron Scattering 2021 delivered by Dr. B.A. Dasannacharya. And this side is the logo of NSSI, and this side the signature of the president of NSSI. And that happens to me, that gives me great pleasure, sir.
It's a pleasure having a certificate signed by you. Grandson.
Yes, sir. Thank you so much, sir. And thank you, Dr. S.L. Chaplot. And here you are hearing Professor Dhananjay Pandey. So thank you so much. No, you are muted. Professor Dhananjay Pandey, you are muted. You are
Yeah.
still muted. We can't hear you.
Now, I had no control actually. I lost control. So I have just got unmuted.
So,
If you permit me, I want to add a sentence
sure.
in a minute. See, I forgot to mention that Dr. Dasannacharya headed this Inter-University Center for DAE facility, IUC DAEF, which is now named as Center for Scientific Research of DAE UGC DAE. But much more than that, when this whole concept was being discussed, he was the prime mover of it. The concept of inter-university center, along with Professor Bhide, he was the prime mover. And but for him, it could not have happened. I remember the first meeting which was held in BRC, and the pivotal role that he played in the establishment of this inter-university center. This was unforgettable. And then, of course, as director, he nurtured the facilities like anything, and many young people, and especially this powder diffractometer, which I have used, an excellent data quality. He encouraged me last time at CNS that please use this, and I used it, and I have published one paper in Physio. It was referred for PRL to 2 rounds. Finally, it came as a comprehensive paper in Physical Review, about 16, 17, 18 pages. It's a very new result. Vasudev has a copy for this. He is a co-author, so he provided the data. So I thank you for encouraging me all along for doing neutron-based research along with other things. And also in my personal life, you encouraged me to take up many responsibilities from time to time. So thank you very much.
Thank you. Thank you, Professor Dhananjay Pandey and Dr. S.L. Chaplot for conducting session. May I request Chairman to conclude and close this session?
Okay. So, Dr. Chaplot.
Yeah, thank you, Professor Pandey.
Yeah, my pleasure.
And of course, thank you, Dr. Dasannacharya.
Thank you.
I don't think the 2 words are enough to convey what exactly we feel. But
Thank you.
we do hope that these kind of occasions will continue.
Thank you.
Thank you, Dr. Chapler. Now, I wish Dr. Dasannacharya please be around. On behalf of all of us here, President NSSI, Dr. S.M. Yusuf, would be handing over a token of appreciation.
This is registered on a photograph. Thank you very much. Again, second time, I wish to thank the Neutron Scattering Society of India, Dr. Yusuf, Dr. Chaplot, who have been president, past and present president, and its president-elect Dhananjay Pandey, who was the first center director at Bombay of IUCDAEF. So he was part of IUCDAEF at one point of time in an official way for a year or little more than a year. Thank you very, very much. This is a prized gift to me from my near and dear ones. And that is the most that I can say. Thank you very much. Thank you very much, Tamara. Thank you.
Thank you.
Thank you very much. Thank you.
Now you can take your seat. No. You're the member of NSSI. Yeah. Is he or he not?